1 to 1/2, get 3 halves, right? You have to put the reciprocal out front. And then in front of, or on the side of that, I put the evaluation bar 0 to 9. Now I'm going to have to plug in 9 and then plug in 0. You have to do it in that order, right? 9 goes in first. So this is 2/3, 9 to the 3 halves, and then 2/3, 0 to the 3 halves. This is just 0, right? That's just 0. What does 9 to the 3 halves really mean? You can look at it two ways. It's either the square root of 9 cubed, or if you want, you could do 9 cubed square root. Doesn't matter what order you do those in. Which one's easier? Square root of 9 cubed, right? Square root of 9 is 3. 3 cubed is 27. So this becomes 2/3 times 27, right? 2/3 times 27. And what's that? Does that go in there? Yeah, 18. Okay, 18. So your final answer is 18. All right, sure. If you say so. So look, I mean, really, at the end of everything we've done here, there's really no new, the only new thing is that now we're going to do something with that antiderivative, right? Like, we're going to be asked to find antiderivatives, which we know how to do. We're all experts at all these different techniques. But now once we get it, we plug in 2 numbers into it and we get a numerical answer. That's it. That's the only new additional thing we have, right? So that's good, I think. All right, I want to do another one. We're gonna. When I put this up here, you're gonna be like, what? What? We can't do this. There's no way we can figure this out. Prove the area of a circle of radius r is pi r squared. We all know that to be true, right? We all accept that as the truth, right? The area of a circle is pi r squared. Prove it. Prove it.
What?
We can't, thank you. That does seem like a stretch, huh? To be going from that problem to this, right? That does seem like a stretch. So maybe what we should do first is we should make sure we understand what that circle looks like geometrically. Circle of radius r, I don't know. Just draw a circle at the origin. Let's say it has a radius of r. That's a pretty good circle. That's what we have, right? What is this topic about? What is this whole thing we've been talking about today about? Finding areas under curves, right? Under functions. Is a circle a function? No, it fails a vertical line test. Do you know the equation of this circle? It's the equation of any circle centered at the origin. We should probably recap this. If you have a circle, this is pre-cal, by the way. If you have a circle centered at HK with a radius of r, the equation of the circle is x minus h squared plus y minus k squared equals r squared. Pre-cal. That's the equation of a circle centered at HK with a radius of r. Does that look familiar? No? Doesn't? Okay. That's the equation of a circle centered at HK, radius r. What is our center in the picture I drew? The origin. So 0, 0, replace this with 0, and you get what? So for this one, it is x squared plus y squared equals r squared. Okay? Do y'all agree that's the equation of that circle? Okay, we already know it's not a function, right? Because it fails a vertical line test. However, could you solve that for y? Could you? Try, at least. Solve this for y. You get that, right? Just move the x squared over. And then to get y, you would have to come in and do what? Square root both sides. And if you do that, what do you have to include? If you take the square root, plus or minus, okay. So we actually have two functions, don't we? We have the positive root and the negative root. The positive root draws what? The top half, and the negative root draws the bottom half. So, and if you didn't know that, it's okay, I'm telling you right now. So this top half of this circle is the square root of r squared minus x squared, and the bottom half of the circle is drawn by the negative root. Negative square root of r squared minus x squared. So is the blue curve a function of x? The blue one, yes? Is the red one a function of x? Yes, separately they are functions of x, right? So I'm trying to find the area of the whole circle. What could I do? Okay, we could find the area just working with the blue, and you want to do just quadrant 1? You just want to do this? Is that what you said?
Because wouldn't they cancel if we use quadrant 1?
If we use quadrant? No, because the blue is a curve. They wouldn't cancel because they're above. I think what you're thinking is if we use this quadrant and that quadrant, they would cancel.
So is the x, the x doesn't become negative?
No. No.
Okay.
Because it's always the width of it is always b minus a. In that formula is b minus a, so it's always the right endpoint minus the left, which will be positive.
Okay.
Good question. So, was there another question? No? Yeah, we could find the area under the blue and just multiply by 2, couldn't we? The area under the blue and multiply by 2. Could we find the area of just the first quadrant and multiply by 4? Yes, we could do that as well. I actually prefer that way, and here's why. If I just try and find this area right here, what's my left limit of integration, my lower limit of integration? 0. My upper limit is what? R. As opposed to if I do the whole thing, it's going to go from where? Negative r to positive r, which is okay. I would rather have 0. I like to have 0, and 0 is easy to plug in, right? So y'all see what we're doing? We're going to see if we can't figure this integral out. What's the integral? I mean, that's it. We have everything we need to set up the integral. We need the area, right? I need the area. Up here comes the integral for the area. Starting at 0, ending at r, right? Starting at 0, ending at r. What's the function? What's the height? Square root of r squared minus x squared, right? dx. dx. Right? That right there is the blue function right here. We're trying to find the area underneath that, just between here and here, and we're going to multiply it by 4. Yes? We wouldn't be proving it's pi r squared. We'd just be proving that the area of a circle of radius 1 is pi, right? I'm trying to make it for any circle so that we get that formula right there. Make sense? Okay. Is there another question? Okay, what's our variable? X. R is a what here? It's a constant, right? Like somebody would give us the radius of the circle. Right? What's the radius of a circle? What's the area of a circle of radius 3? They give us r, right? So r is a constant here. X is the variable. Do you all know how to integrate something like this? Yes? How? What? Trig sub. Trig sub. Right? Isn't this trig sub? Do you see a square root? Do you see a squared minus x squared? It's not really a squared, it's what? R squared? But isn't our formula, that's our constant, right? So this is trig sub. So look, I've got to find the antiderivative now. Do you all agree? I've got to find the antiderivative, and it's not going to be as simple as the problems I gave you. I have to actually work on that antiderivative a little bit, right? So I'm going to stop the problem here, and I'm going to come over here, and I'm going to do this. Because I realize right now that I've got some work to do, right? I realize I've got some work to do. So I'm going to come over here and I'm going to say, all right, I need to do this. I need to do the indefinite integral to find the antiderivative. Once I get that, I'll come back over here. I'll slap it right here, right? I'll slap that answer right here. I'll put my evaluation bar 0 to r, and then I'll do my work, right? I'll finish the theorem off, or the fundamental theorem. But I need to find that antiderivative. I'm going to use trig sub. What's the sub? X equals r what? Sine? R sine theta. I'm going to replace all my x's with r sine theta. All right, dx would be, take the derivative, r cosine theta. D theta, don't forget the d theta. And then what does the square root of r squared minus x squared turn into? I won't show the work. Yep. And at the end, when it cleans up, it'll turn into r cosine theta. I'm not showing that, okay? Is there a question, Chris? No? You all right? Okay. Y'all know what I'm doing? Trig sub here? I'm not showing that work. Rewrite the integral. What does the square root of all that turn into? This right here is r cosine theta. What does dx turn into? R cosine theta d theta. Right? Dx, right? Dx is this. The square root was r cosine theta, is that, right? All right. What can come out of the integral completely? Well, that's a good sign. Isn't that a good sign? R squared, because what's the area of a circle? Pi r squared, right? So r squared's coming out. Integral, antiderivative. I have inside here what? Cosine squared theta? D theta? You know how to deal with cosine to an even power? Power reduce? Power reduce, half angle, however you want to look at it. So this becomes 1/2, 1 plus, minus, plus minus, plus cosine 2 theta. Didn't I promise you on your next test you're going to have to be able to do that in the test? I did promise that. All right, I can pull the 1/2 out. R to the r, sorry. R squared, integral 1 plus cosine 2 theta d theta. I need to separate this. I'll come back to that. All right, let's do, I think we can do our antiderivative now, right? So 1/2 r squared, antiderivative of 1, theta. Okay, this we've done a few times. It's 1/2 sine 2 theta when you do that antiderivative. Then plus c, because I'm doing an indefinite integral right now. We have to get everything back in terms of x now, right? Everything back in terms of x. 1/2 r squared. Okay, what's theta in terms of x? How do you do this? How do you get to theta? Yeah, you have to take this, solve it for sine theta, and now take inverse sine on both sides. So this will be inverse sine of x over r. And then do y'all remember what happens here? We use the identity, right? This is 2 sine theta cosine theta. Twos cancel. So you need plus, you need sine theta cosine theta here. You need a reference triangle, right? I realize this is, quite a bit of stuff we're having to do here, but we are also trying to prove that the area of a circle is pi r squared, which eluded humans for centuries, right? All right, so I need my reference triangle. What does my reference triangle look like? I'm going off of this right here, right? Theta is x, let's see, sine is opposite over hypotenuse, so this side is, oh, I just got that wrong, sorry. R squared minus x squared. There's my reference triangle. We're almost there. 1/2 r squared, okay, inverse sine of x over r plus sine theta, which is x over r, times cosine theta, which is square root of r squared minus x squared over r plus c. That's the antiderivative, right? Now I'm ready to go back to the fundamental theorem of calculus. I'm trying to find the area under that, and now I needed the antiderivative, then I got to plug in r and plug in 0, right? So let me continue this, but over here. Are there any questions before I erase this? All right, so here's where I am. I needed the antiderivative, which we just got to be 1/2 r squared in front of inverse sine of x over r plus x over r. Can I write it this way? Can I write x square root of r squared minus x squared over r squared? Is that all right if I just put these together? Just put these together? I don't need a plus c, do I? No. But now I need my evaluation bar. 0r. So what I was doing was I was continuing this now, right? I was continuing this. So now I've got to plug in, right? What gets plugged in first? R, right? So this equals, I'm going to plug in r and subtract when I get what I get when I plug in 0. All right, let's plug in r. 1/2 r squared sine inverse of what? R over r, right? I'm going to put it r over r plus, okay, what happens here? R square root of r squared minus what? R squared, that's 0, isn't it? All over r squared. Okay, that's plugging in, I think I need another parenthesis here, hold on. Yeah. All right, that was plugging in r. Now let's plug in 0. I just want to show you everything getting plugged in. Lots of good things happen here. What is this? 0 times, who cares, right? 0 on top, r squared on the bottom, gone. This is a 0. What is inverse sine of 0? So at what angle on the unit circle is your y coordinate 0? 0. What is this? Well, that's a 0, isn't it? 0 times whatever divided by r squared? 0, right? Lots of things are going away here. All right, this one right here. What's inverse sine of 1? So at what angle on the unit circle is your y coordinate 1? Pi over 2. So this is, we're at the final answer. Well, not final, but we're at the result of this. This is going to be 1/2 r squared times pi over 2. Right? This is pi over 2. And everything else went away. So all you have is 1/2 r squared times pi over 2, which is the same as r squared times pi over what? 4? That is the area of the first quadrant. Just the first quadrant. So we need to take that answer and multiply by 4. And when you multiply that by 4, you get pi r squared. See that? So what we said here is that this quadrant right here was pi r squared over 4. And now you just multiply by 4, and we've proven that the area of a circle of radius r is pi r squared. Didn't think we were going to do that today, did you? All right, so where are we going with this? We got 15 minutes. Well, we need to move on, okay? There's other examples we could do, but I need to get to the properties. And so I'm going to kind of walk over to the board and discuss, well, no, I won't. I'll do them up here, but I need to discuss these properties with you. When's our test? 23rd. Is that, how many weeks is that? I didn't give you all anything for it yet, right? No, okay. Week and a half? Okay, I'll give you something next week. Okay, so properties of definite integrals. Look at that first property, if you can see it. It says that if you want to do an integral, the area under a curve, and you want to go from A to A, so that means you don't have an interval, right? Like you don't have any region. So the answer naturally should be 0, shouldn't it? So that's like you're trying to find the area underneath some function, right? But your interval is only from A to itself. So it's like you're trying to find the area of a line, basically. And lines don't have areas. So the answer should be 0. That's the first property. What does the next property say? The integral from A to B of some function, so the area under that, is equal to negative of the integral from B to A of f of x dx. All this means is that if you reverse your A and B, if you change the order of integration, if you change your limits of integration, the only impact it has is it changes the sign of the answer. And that does become useful later. It's just a property we need to establish. What that basically does is that by switching these, it changes your dx to always be the other way around. So instead of b minus a, it's a minus b, and it just changes everything to opposite sign. That's your next property. All right, the third property, not used very often, so I'm not going to do it. Fourth property, I'm not going to write on the board. What does the fourth property say? You can pull a constant out. Now, I've done it already, but that's just the property. This is just saying that you're allowed to, okay? Like for sure. You can pull constants out, right? You can pull a constant out. Okay, this next property is really kind of, it's intuitive, but I just want to make sure you understand it. The first thing it's saying is, look, if your function is always what? If your function is greater than or equal to 0, which means if you draw it, it's what? Above or possibly touching the x-axis. So if you have a function that does this, maybe it touches, but never goes below, right? And you want to find this area, what can you tell me about that area? It'll always be positive, right? Or possibly 0. The only way it would be 0 is if this was just flat. But if your function's always above the x-axis, you should expect a positive area. Similarly, property 6 says if your function's always below the x-axis, you should expect a negative answer for the area. And remember, these are all in your notes. You can go back and look these up. Look at property 7. 7's going to be an important one for us. Property 7 says that if you have an interval that you're looking at where your function goes from A to B, and then there's some C somewhere in the middle, that if you want to know the area of the whole thing, right, you can actually break it into two areas. You can do this one, and then you can split it up and you can do the other one. And that's what those two integrals represent. You'll see? if you want to go from A to B, right, all the way from A to B, what you can do is first go from A to C, find that area, and then go from C to B and find that area. And this picture is, the same idea. If you want to find the total area, you can find just the green and then the yellow, add those two answers. Do y'all know what even functions look like? A function is said to be even if it's a reflection of itself over the y-axis. Look at that function. Is that a reflection of itself over the y-axis? Yes? So look at what this property says. It says if you have a function that's a reflection of itself, then if you integrate from negative a to a, that means negative a to positive a. That has to be the same number, just opposite signs, from here to here. That's the same as going from 0 to a and doubling the answer. Because it's symmetric. It's kind of like what we just did with the circle. Instead of going from negative r to r, we went from 0 to r in, well, we quadrupled it because it was in all 4 quadrants. But that's the same principle.
Same thing with sine.
Pardon?
Same thing with sine, what we did.
Yeah, with sine, it would, yeah, but that's not, yes, that. Sine's not even though. But we did the symmetry. We used the symmetry. What if it's an odd function? Do you know what odd functions look like? It's a reflection over x and y. Here, let me give you an example of an odd function right here. That's an odd function. So what if I went from negative a to a? What could you tell me the area should be? 0. Why? Because they're reflections, right? But this part's positive, this part's negative, right? Positive and negative. So we should get this to cancel that out. As long as we're going from negative a to positive a, then we should get cancellation. That's the next property. Cancellation equals 0. All right. That is the correct homework assignment. So what I'm asking you to do there is to go back and look at some of your old problems that you did already. Do you remember during your problems I told you if it had numbers, ignore the numbers? Well, now you can plug the numbers in, right? You found the antiderivative. You just need to evaluate. So practice evaluating antiderivatives. How are we doing on time? Yeah, you know what? This is a good natural breaking point. I don't think we should start. Where are we headed? Into the abyss. No, we are headed into more complicated stuff now, right? And it's going to get, pretty quickly we'll move through some new ideas. All right? What are you going to do this weekend? Homework and review maybe? This is a good opportunity for you to start thinking about what's going to be on that next test, which means you should start looking at your homework, your lecture notes, everything, right? Remember, the next test will not cover anything that was on that first test. Like, I mean, some of it is built in, because that first test had, what did it have on it? Basic U substitution, a little bit of integration by parts. Like, all that is like pretty straightforward now for us, right? Hopefully. Okay, everyone, have a great rest of your day. Stay out of trouble. Have a good weekend. Oh, and I may not be able to be in my office today. I just found out that my daughter gets out at noon today, and I didn't know that.
Oh, with the early release stuff?
No, she's in a private school. They're doing PSAT testing, and they're like, yeah, so I just got that word. So because of that, I might have to bail out of here as soon as my other class is over. So if you go by and I'm not there, just sorry. Excuse me.